Hey everybody, and welcome to your first online lecture for Bio101 Biology. Today I'm Mary Annarella, your host, your professor, and I'm really excited about this semester, and I'm really excited to be sharing with you basics in biology as well as things that develop throughout the semester. After all, this is called Biology Today, not Biology Yesterday, although we certainly need to do a little bit of yesterday's stuff so that we can build on our knowledge. Anyhow, so I usually start off the class just generally talking about science because today in biology we know so many more things and have much deeper understandings of human health, for example, than we did 100 years ago. But scientists have been testing and studying the natural world and our bodies for 1,000 years. So I want to just start off talking about how we know what we know. How do we keep building on this body of knowledge that we have, and who gets to decide what we know? Who gets to decide what's inside a cell? So to do that, I want to talk a little bit about the difference between a couple of different things. Like in science, you've probably heard of these things called scientific theory. And I did it again. I started doing this in portrait mode and I want it to be in landscape. There we go. Now you can see things a whole lot better. Okay. So in science, we have these things called scientific theories, a scientific theory. Stuff like the theory of evolution, atomic theory, germ theory, stuff like that. But we also have these things called scientific laws. We call a scientific theory a theory and a scientific law a law. I guess I should get my tenses here together, get them jibing, because they're not the same thing. These terms are not interchangeable. A scientific law and a scientific theory are not the same thing. So I'm just wondering if you can think about what the differences are between these two. And if we were in person, I would have everybody brainstorm some stuff. Like, can you name some different scientific laws that you've heard about or had to study in the past? And sometimes, usually one that comes up is, the law of gravity. Okay, we got that. The law of gravity, which states what goes up must come down. Sometimes someone will come up with, Newton's laws. Newton's laws of planetary motion. Planetary, I can't spell today. Newton's laws of planetary motion, which describe the arc of the planets and the like. Pardon me. If you can think of any other laws like in physics and chemistry, oh my God, chemistry is just full of them. Things like the ideal gas law, Boyle's law, stuff like that. They're often represented by equations like the ideal gas law is PV equals nRT. We are not doing that here. This is biology. This is not a chemistry class, not a physics class either. Physics, the laws of physics. There are so many different laws of physics, like the law of inertia, which states that a body at rest will stay at rest, tends to stay at rest unless acted upon by an external force, and a body in motion tends to stay in motion unless it's acted upon by an external force. It's why it's hard to get up in the morning. It's inertia. There are a bunch more. If you can think of some, let me know. Jot it down. Scientific theories, though. Let's say, the theory of evolution is one that comes up, which states that, which explains why things change over time. Einstein's theory theory of relativity, which explains how small particles of matter behave. That's the E equals mc squared thing. There is atomic theory. Oh, germ theory. We could go on and on. Oh, the Big Bang theory. Our whole universe was in a hot, dense state. I loved that show. It was mindless and fun. It's still my go-to happy place when I need something to watch. Just want to be happy and laugh. Anywho, I'm doing this because I want to talk about, well, what do we think a scientific law is and how is it different from a scientific theory? And sometimes a lot of people will say, scientists I've talked to would even occasionally say this. And they would say, well, a law is proven, but a theory hasn't been proven. And the answer to that is, we need a new color for this. How about purple? Nope. A law isn't proven and a theory not proven. It's not how it works. The law, a scientific law, is an observation of something in nature, of something in the physical world. Whereas a scientific theory with a capital T is an explanation of the law. It's why the law is what it is. So, for example, the law of gravity. The law of gravity says that if things go up, they must come back down. It doesn't say why things come back down to earth when you toss it up in the air. If I hold my little stylus, my pen here, and I let go of it, you know it's going to fall right to the ground, period. We observe it over and over again. But why that happens is a theory. So there actually is a theory of gravity as well. That explains why things come back down to earth, which says that, oh, well, there is a force created by a large massive body, the body of the earth, that creates a force that we're going to call gravity, the gravitational force that pulls everything towards the center of this massive planet. It explains the law. As another example, here's an observation that says, Darwin, for example, noted that the diversity of species changed over time. Diversity of species in an area, in a location, changes over time and is different from one area to the next, and is often different from one area to the next. That is just an observation. Hey, I noticed that these plants grow on this island, but they don't grow on another island, and there's different stuff living there. Darwin made that observation. So the law there would be that things change over time. The diversity of species changes over time. The explanation as for why that happens, why things change over time, is the theory of evolution. The theory of evolution. And the theory of evolution basically states things change over time because of natural selection or genetic mutation or something called genetic genetic drift, that sort of thing. So the theory just says, oh, well, natural selection means so things change over time. One of the reasons that things change over time is that the environment naturally selects for what plants and animals can live in this particular area. For example, you do not have orange trees growing in the wild up here in New England because the environment selects for that. The environment here selects for things that can survive a cold winter. You don't have that in Florida or in Southern California. That's why oranges can grow there. You don't find them here. We have a different diversity of species up here at our latitudes than they do in Florida and points south, closer to the equator. So that's natural selection as an explanation. It is a theory. But here's the deal. There is a difference between theory with a lowercase t versus theory with a capital T. A theory with a lowercase t, and any Yahoo can come up with that. I could say, well, I have this theory that it gets dark at night here because the world is on the back of a giant turtle. I can just make that up. That might be my personal explanation, but I have no data backing that up. In order for something to be accepted as a theory, as an true explanation in the scientific community, in science, it has to be backed up by a tremendous amount of data. Backed up by a lot, that's what these little arrows going up to the sky are for here when I draw those. Backed up by a lot of scientific data. Data that's been peer-reviewed and repeated by others. All right, so I'm pointing this out because things like, the theory of evolution, germ theory, which states that human disease is actually caused by pathogens, by microbes we can't see. This is accepted as fact in the scientific community, that microbes can and do cause human and disease. Atomic theory states that matter is made up of small things called atoms, and that those atoms have electrons and neutrons and protons inside of them. No one has seen a proton, but we have tremendous evidence that backs this up. Atomic theory is backed up by a ton of scientific data. No one is refuting the fact that matter is made up of small particles called atoms, and inside those atoms are these subatomic particles called electrons and protons and neutrons. They are accepted as fact because they are backed up by a tremendous body of scientific data, not just a couple experiments, but over years and years and years of scientific testing. Let's see. So when people say, well, the theory of evolution is just a theory, well, that's like saying that the Taj Mahal is just a building. Yeah, it's a building, but it's an incredible one. It's elegantly constructed. And the theory of evolution, as well as what other theories that we accept as fact in the scientific community, are backed up by so much evidence. And if there is any evidence that shows up that contradicts it, we have to go back and revise the theory. If your data contradicts your theory, you have to go back and alter your data. You have to repeat that experiment, make sure that your data holds up. I want to point this out, too, that a law, it's not like human laws, like we make law, a bill becoming a law. A law does not ever become a theory, and a theory does not ever become a law. It's like they don't graduate. We're not like, oh, well, the theory of evolution, that's so good, we're going to call it the law of evolution. No. Theories and laws are not the same thing. They can't be, because the explanation Oops, why did I do that? There we go. The explanation of the observation can never become the observation. It's an explanation. It can't become the observation. They're two different things. It's like saying an apple becomes a table. They're two totally different things. All right. So let's get into a theory, germ theory. Germ theory states that microbes can cause disease. You know, 1,000 years ago, people are like, it's bad air that causes disease. And well, yeah, you can breathe something in the air that can make you sick. Sometimes it's a microbe in the air that you breathe in and it makes you sick. It's not, not people used to believe, thousands of years ago, well, if someone develops an illness, they must have done something wrong in their lives. They must be bad people. They must be sinners. No, no, that microbes can actually cause disease. And Louis Pasteur was the first person to postulate that. Louis Pasteur. Let's see. Another one is cell theory. That living organisms, what makes an organism a living organism is that they are made of cells. Organisms are life, and organisms are made of cells. Cells. This was controversial way back in the day. Right? We accept that life is made of cells, that our bodies are made of collections of cells that work together for specific purposes, and we call those specific purposes, cells that work for specific purposes, organs in our bodies, for example. Okay, so with cell theory, we organize all of life. Organize and categorize life and living organisms. And you've probably heard of the whole kingdom, phylum, class, order, blah, 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 blah. I'm not going to worry about kingdom, phylum, class, order, family, genus, species. The important one is actually above the level of kingdom, and this is the domain. So it's actually domain to kingdom, to phylum, to class, to order, family, genus, species. I want to focus on the domains because there's a lot of arguing in the scientific community about the kingdoms, and we've changed them so many times that it's just kind of a pain in the butt. The domain system uses genetic sequence data to show relatedness between different organisms. So the domain system has what we call 3 domains. And the 3 domains are eukarya, bacteria, and then, oops, I misspelled that already, archaea. And sometimes it's called archaebacteria, but let's just call it archaea. All right. Eukarya, and you've probably heard this word before, every organism in eukarya is eukaryotic. That means cells that have a nucleus and what we call membrane-bound organelles. So if something is in eukarya, it's a eukaryotic cell. Bacteria, let's get a different color for bacteria, shall we? Here we go. Are prokaryotic cells. And so are archaea. They're prokaryotic cells. Prokaryotic cells have no membrane, no nucleus or membrane-bound organelles. No nucleus, or I'm just going to write organelles here. We'll see what organelles are later in the semester when we study parts of the cell. But that's a major difference between eukaryotic and prokaryotic cells. Bacteria are all unicellular organisms, and so are archaea bacteria. They are unicellular. So far I'm not seeing any difference between bacteria and archaea. There is a difference. We will get there in a moment. Back to purple. Eukaryotic cells can be unicellular or multicellular. All right, so try to come up with a Venn diagram for this, in your head. If something is unicellular, do we know if it's bacteria, if it's archaea or eukarya? Don't know, because there are unicellular organisms in all three of these domains. But if something is multicellular, only eukarya contains multicellular organisms. So me and you, our dogs, our cats, mosquitoes, they are all eukarya. They are multicellular and therefore eukarya. But if I tell you, oh, I know this organism and it's unicellular, you don't know which one of these it's in. You need more information. If it's a unicellular eukaryotic cell, say that 3 times really fast, then you know it's in eukarya. If it's unicellular and prokaryotic, you're like, well, it's got to be either in bacteria or archaea. I don't know. Okay, so what is the difference between bacteria and archaea? There is one major difference, and let's go back to blue, I guess. Everybody in the domain bacteria has something called, a substance called peptidoglycan in its cell wall. It's a substance that's a carbohydrate, but guess what? Archaea bacteria don't have I'm running out of space here, peptidoglycan at all. So that's your major difference there. You're probably familiar with bacteria. Probably some of you have had a bacterial infection at some point in your life, an ear infection, or strep throat is a bacterial infection. Nobody gets infections from archaea bacteria. They are really weird cells, and they live in very extreme environments like hot springs, deep within the earth, 2 miles under the floor of Boston Harbor, way down there in the mud, a couple miles down. Weird stuff. They're weird. And they live in extreme environments. They really do. Okay. Now you may notice that I left something out here. What about, let's get a third color going. How about green? What about viruses? What about them? Where do they fit in? Guess what? Viruses don't fit in to the 3-domain system. They're not eukaryotic cells. They're not prokaryotic cells. They're not, we actually don't consider them to be living organisms. They are what we call obligate intracellular parasites. Obligate meaning necessary. Intracellular, meaning they have to get inside your cells. They have to get inside a host cell in order to make more of themselves. They can't reproduce on their own. They have to get inside your cells or, some host cell in order to make more of themselves. So a viral particle sitting out, on someone's desktop for years is going to die off. I mean, yeah, they last a couple hours. Coronavirus might last as long as a day or even 2 in some instances. It's postulated. But it can't make more of itself there. It's eventually going to die. It can't reproduce. So that's part of the definition of a living organism. It has to at least have the machinery to reproduce itself. Yes, I know that there are organisms in eukarya and bacteria that live in symbiosis with other organisms or actually are parasites, like tapeworms. But tapeworms actually have the cellular machinery to be able to make more of themselves. They've just kind of lost the ability to use them. Viruses don't even have the machinery to be able to do anything. They have to get inside your cells. So must get inside a host cell. And just because all the little icons for viruses are a brighter green, I'm going to go with that. So let's talk about what makes a virus, because I want to be able to talk about coronavirus. A virus, at its most basic level, is just DNA or something called RNA a DNA or RNA genome, so a little piece of DNA. There we go, draw it there. Or in the case of coronavirus, it is RNA. And 2, a protein coat, which is sometimes called the capsid. So a protein coat. I'll draw it like this, because some viruses are actually shaped like a hexagon. So there you have it. There's a virus, a viral particle, all by itself. Things like coronavirus actually have some extra stuff to them. So, like, it has this fluffy outer layer on it, and sometimes it's called an envelope. And coming out from the coronavirus, I'll draw it like this, and you've probably seen this a lot, are these things that are called the spike protein. There. And you've probably heard that it's the spike protein that is like the key that gets this virus, gets SARS-CoV-2 into your cells. So yeah, here, let me write down that this is SARS-CoV-2. It stands for severe acute respiratory syndrome coronavirus number 2. SARS is SARS-CoV-1. This coronavirus is SARS-CoV-2, which causes COVID-19. So COVID-19 is the disease, right? But SARS-CoV-2, come back, is the virus. So just to clean that up a little bit. But it's the spike protein that is the key that fits into basically a lock that's on your cells. Let's say this is a human cell. I'll give ourselves a nucleus there and a whole bunch of other stuff, some mitochondria, all these things that we'll study there. But on the surface of our cells, we have these proteins, and this one is, in this case, it's called the ACE2 receptor. And what happens is that the little coronavirus, with its spike protein, can bind. Its spike protein binds to the ACE2 inhibitor. The ACE2 receptor. This causes the cell to open up and pull the virus inside. The virus is much smaller than this compared to your cell, way smaller. Probably compared to our cells, it's probably like that. Okay, but I just drew it bigger because, like, this is the whole thing right here. It's probably more like that. And it gets it inside your cell that way. Once it's inside your cell, it can start taking over your cell's machinery and say, ha ha ha, you must do my bidding. And that's basically how it works. It takes over your cell machinery, and then it gets more of itself made inside human cells. So imagine, okay, I'm getting really sloppy here with drawing my coronaviruses, but imagine it taking over a human cell and turning that cell into a little viral particle factory. And then what it can do is tell your cell to release all of these viral particles. Now I'm getting really sloppy with drawing my viral particles here. And releasing them, out into the mucus in your lungs and nose, and then you cough and sneeze on somebody else, and this viral particle goes and finds your friend's nose and gets in there. So that's why we're wearing masks, to prevent transmission here. Okay, so let's see. So viruses, take-home message, they don't count in one of the domains. We don't consider them to be living organisms, but wow, it's kind of weird, that we don't, because they certainly know how to assert themselves, don't they? They are obligate intracellular parasites. They get inside your cells. What lets the SARS-CoV-2 virus get inside your cell is this spike protein binding to the ACE2 receptors on the surface of your cells. They get inside your cells, make way more of themselves, and that's what causes problems and usually often clinical disease. So your body has some defenses for being able to fight off a viral infection like that, right? Like you've probably heard about people talking about these things called antibodies. The human immune system will make antibodies against what it sees as a foreign invader. So these are proteins of the immune system that are made in response to what we call an antigen. Now, what is an antigen? Okay, if you look up in the glossary of an immunology book, it'll say an antibody is immunoprotein that is made in response to an antigen. And if you look up antigen, it'll say it is a molecule that cross-reacts with an antibody. Like, all right, this is not helpful. An antigen is any molecule that the immune system recognizes as not self. And in the case of SARS-CoV-2, it's generally the spike protein that the immune system is like, what the heck is that? What is that? Quick, make antibodies against it. Antibodies are usually Y-shaped like this. And your cells will make a whole bunch of antibodies against it that kind of tag this virus, and it basically tells your immune system, hey, everybody get over here and destroy this thing. These are what we call neutralizing antibodies. Neutralizing antibodies. But here's the deal. If you get infected with SARS-CoV-2 and your cells make antibodies against this, we don't know how long they last. There is evidence that shows that antibodies against coronavirus in those in COVID-19 patients only last about 4 to 5 months, tops. See, could get it again or catch the new variant, one of the new variants that's out. So what we need is a stronger immune response. And also, just because somebody gets infected with coronavirus here, I'm here inside the cell here now, and your body makes antibodies to it, that doesn't mean you're not going to get sick. So you made antibodies, but you still got COVID and you still wound up in the hospital and ended up with lung damage or heaven forbid, kidney damage, or reactive arthritis as you are recovering from it. Real drag. I mean, people are ending up with lots of health issues as a result of this. So it's like your antibodies didn't do you any good. The idea behind vaccination is to trick your immune system into making antibodies against, for example, this little spike protein before you get exposed, before you get infected with SARS-CoV-2. All right. Need a better color here. Let's go to orange. We haven't used that yet. All right, so vaccines. A vaccine is defined as a preparation of a pathogen Oh, and by the way, a pathogen is just a microbe that causes disease. A preparation of a pathogen or its parts, and this is very important, or its parts, in order to induce immunity without causing illness, without causing disease. So the idea behind a vaccine is to somehow present the human immune system with maybe just part. Why is this? Shucks, my stylus isn't working. I need to charge it again. And we're back. My pencil is hopefully working again now. Recharged it. And we're back, and my little eye pencil is charged again, so we can get back to business here. Gosh, I started started recording the screen again. That's when my mother called, even though I have my iPad on airplane mode. My phone was not, and it's sitting right here. Gotta correct that. Anywho, a vaccine is a preparation of a pathogen or its parts in order to induce immunity without causing disease. So, for example, the polio vaccine. The polio vaccine is given to people in order to prevent them from getting an infection with the polio virus and not getting that disease. Polio is the disease that Franklin Delano Roosevelt famously had. It crippled many people, and not only were people limited to being in wheelchairs, but oftentimes people would lose the ability to breathe on their own, and they'd have to breathe in an iron lung when the polio, when their disease was at its worst. So yeah, we do that. Better example, how this all got started. For example, there is a disease called smallpox. I'll let you Google that because I don't actually have my Safari all set up without you seeing all my other stuff on here. But smallpox is a disease that is very severe. Very severe. You get covered with blisters. People die of smallpox. Smallpox has been a pox on humanity for thousands of years. We are finally to the point where we have mostly eradicated the smallpox virus from the planet. But way back when, in like 1780, I want to say, 1780 in England, there was a British country doctor called Edward Jenner. Jenner was the dude's last name. And this little story, I want to preface this by saying that this practice that Jenner, quote unquote, discovered had been practiced in other parts of the world for thousands of years already. Jenner was just the first person to document this scientifically. So he ends up getting credit for it, but we'll get to that a little later, give him some more credit where credit is due to. But Jenner, back around the 1780s in England, noticed that milkmaids, 8 maids a-milking, milkmaids, maids who would go and milk the cows, milkmaids who got a disease called cowpox. It was a disease that people would pick up from a cow, cowpox. And milkmaids who got a disease called cowpox didn't get smallpox. So, okay, we need a different color for a cow. I don't know how to draw a cow. My cow. Oh my God, my cow looks like a dog. This is terrible. I cannot draw cows. Let's draw maybe the spots. I don't really know what cow ears look like, I guess. This is not my area of expertise, art. Okay, let's say this is a cow. All right. Cows would get a disease that we called cowpox that was kind of similar to smallpox. And when humans would get it, let's put the milkmaid in blue. There's their little milkmaid hat. And we'll let her carry a bucket of milk. Okay, they'd get cowpox from the cow. I'll put a little spot on there from the cow. And the thing is, they would get cowpox. Cowpox, can't spell today, can I? They would get cowpox, but cowpox was really, really mild. It was a very mild disease compared to smallpox. Smallpox was severe disease. Cowpox was mild. So most people would be like, hey, I'd much rather get cowpox than this smallpox thing. But the thing is, people who worked with cows who caught cowpox didn't get smallpox. And this dude, Jenner, noticed that going on. So he's like, I'm going to do me an experiment. And I'm going to do something that the FDA would never allow you to do anymore, because there's this thing called informed consent we have. Thank God. He took pus from a blister on a milkmaid. Oh, and gosh, this is so funny. The milkmaid's name was Sarah Nelms, and the cow's name was Blossom. It's so funny. And he wrote this down. He took pus from a cowpox blister. From Sarah's cowpox blister, and basically infected this little kid with cowpox. And the kid's name was James Phipps. And he got cowpox. Duh, no kidding. Then Jenner did something that you never, ever, ever, ever could do anymore. This is horrible without informed consent. I mean, I don't know, maybe he asked the kid's family if it were okay, underage. After James Phipps got cowpox, recovered from it, he challenged him and took pus from a smallpox blister and infected James with it. James did not get smallpox. So they got something that was related to smallpox. Cowpox is a similar disease to smallpox. And something about getting smallpox caused the immune system to make antibodies against it that also worked against smallpox. So let's see. They got cowpox. Their immune systems made antibodies against the cowpox that also worked against smallpox, which was a much worse disease. You didn't want it. This was an early form of vaccination that we call variolation. Okay, things are much better now. We study these things. But the idea behind a vaccination is the same as variolation. To expose people to some form of a pathogen that won't cause disease, or its part of a pathogen, like maybe just exposing people to only the spike protein, not the whole thing of coronavirus. There we go. To give them something that's so extremely mild it doesn't make you sick, but lets you recognize the real thing when it comes later on. But variolation was the early form of this. Now I want to show you something, because I learned this recently, that 75 years before Edward Jenner actually started using variolation to begin basically vaccinating people, helping people to not get smallpox. Okay, 1780s, we had just ended a little war over here in the U.S., as you may know. But way before that, in 1706, there was... All right, so that was variolation. Variolation. It was not invented by Edward Jenner, right? It was documented and tested scientifically by Jenner, but he did not invent this at all. There is a bit of history that I didn't know about, that I only recently learned from a person that I follow actually on social media. Her name's Yvette Cybabe is her handle on Facebook, and I'm not encouraging you or discouraging anyone from following this person, and I'm not encouraging that people take get their information off of social media. Hey, I follow this person because she is into debunking misinformation. She does some research and she is really funny, but please don't follow her unless you are totally okay with profanity. But there was a post of hers that made me dig a little deeper, and even though I know she has fact-checked these things, everything that she posts, I feel the need to fact check myself, and everyone should do this. So I did some fact checking, and lo and behold, wow, I had no idea that 75 years prior to Edward Jenner's little test with Blossom the cow and Sarah Nelms getting cowpox and James Phipps and blah, 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 that there was a man who came to be known as Onesimus. Did I spell that correctly? I'm not sure I spelled that correctly, or if I'm even pronouncing it correctly. Onesimus was an enslaved man who was stolen from what is believed to have been Ghana, modern-day Ghana. And this was in 1706. He was enslaved and sold to a Bostonian named Cotton Mather. If any of you are history students, you might know that name, Cotton Mather, but not the name of Onesimus. Now, we do not know what Onesimus's African name was, and we don't know the exact date of his birth either, but we do know that he was sold into slavery to not to Cotton Mather, he was sold into slavery and given as a gift to Cotton Mather in 1706. And as Cybabe's post says, how very 1700s of them. Horrible, horrifying. Cotton Mather was a preacher, famous Bostonian preacher. And I guess he asked this man who he enslaved now and renamed Onesimus if he had ever had smallpox. And Onesimus said both yes and no. Onesimus had told Cotton Mather that he had some sort of procedure in Africa that was very, very common, where he was exposed to something and then that conferred immunity. So this was the cowpox thing. This was variolation that Onesimus was describing to Cotton Mather. And Cotton Mather, desperate to not get smallpox and not have anyone that he knew get smallpox, decided to start promoting this idea that Onesimus had told him about, this process of variolation. Right there. All right, so these were the 1700s. So people were like, what the heck are you talking about? Cotton Mather was able to convince someone named Dr. Boylston. Does that name sound familiar to anyone who spent any time in Boston? Boylston? Oh, I forget the guy's first name. It began with a Z. Zebediah, that's not right. It's something that begins with a Z. And so Cotton Mather was able to convince Boylston that this variolation thing was legit, but basically no other Bostonians believed him. Mather was actually accused of, cavorting with the devil, and they even tried to threw a bomb through his window, apparently. I verified this through a couple of news articles, one of which was in the Boston Globe a couple years ago. Anyhow, so this Boylston guy of Boston fame, this was during an outbreak in it was a little bit later. It was like 1710 or so. There was a smallpox outbreak in Boston. And out of 11,000 Bostonian residents, and this was the population of Boston at the time, 11,000 people, 844 people died. That is 1 in 7 people who died who were not inoculated with through variolation. Boylston used variolation. And I'm doing it again. Too bad. I'm just going to leave it small like this. I'm sorry. I'm doing portrait. I got interrupted and had to come back and then forgot to turn this. But he used variolation on about 250 people, and only 1 in 40 died of smallpox. So that's what, 2% or something like that? Wicked small number. Yeah. And so it's really not, and this was 75, 80 years before this was before Jenner was even born. Jenner wasn't even born till like 1745. So this was a long time before this. So this kind of gave birth to the vaccination movement in Massachusetts. Apparently, later on, Onesimus was able to purchase his freedom, kind of, sort of. He was able to purchase his freedom with the caveat that he would still be available to work for Cotton Mather, apparently, because 1700s. And he was basically lost to history, were it not for some historians digging a little bit deeper. And he has been named, I think he is named on the list of 100 greatest Bostonians of all time. I read in a news article he's actually number 52. So go, Onesimus, thank you for getting us going and getting us some health care in Massachusetts long before Jenner or anyone had ever thought of it. So that's your moment in history, your moment in science, and I will be back next time. I will have a second video for you all to watch before class on Tuesday. This is just part 1, because I can't talk at you for 2 hours straight without like losing my voice. So this is part 1. I'll upload it. You can watch it at your leisure, and then I'll have another one uploaded for you by Friday. So take care and be well.